Thank you, Jules, and thanks for Juice. So my first talk in 2015, I talked about how we use Juice. I'm not going to talk about that. But I was very inspired by your talk this morning, and here's your diagram. So I wanted to apply this to myself as someone who and thought about my own software, and I realized that basically what I do violates every single criterion for significance. So I thought I would illustrate this. So I work on software that is generally designed for prototyping. So as you heard Friedemann say, Live is an example of something that was in some way prototyped in Max, that Ableton uses Max to prototype ideas for devices. So what, in the context of prototyping, the half-life of any individual prototype could be seconds, possibly minutes. So that doesn't seem very good. Individuals could be one, because it's just for you to like think about your idea. Maybe two if you happen to show your prototype to someone else. Often your prototype basically is for you to figure out that the idea that you had was stupid. And it actually serves a valuable purpose for that. In terms of impact, well, you're probably the only person who's going to be impacted on it. And as I said, maybe the impact is just going to be that this is a foolish idea. By definition, you don't want anybody to depend on your prototype, right? So the number of dependencies and the significance of those should be minimum. And in terms of the energy needed, of course, you're trying to do something as fast as possible, so you don't care about performance or energy consumption whatsoever. So basically, the significance of your code is tending towards zero. So this talk is a little bit of how we're trying to change that a little bit. And I'm not going to go into how the diagram would necessarily change. That's probably a different talk. But and I also hadn't seen this diagram until this morning, and Jules was nice enough to send it to me right after his talk, so I could include it. But it's definitely something to think about as you're hearing this presentation, which is not, I should say at the beginning, I'm not suggesting that you actually go out and use this thing that I'm making, but more, I thought it might be interesting to look at it on a conceptual level and maybe inspire you to think differently about problems that you have. So last year, my talk here at ADC was about this thing which we released about the same time called the blocks package. So Max has this thing called a package manager where externally developed software can be easily downloaded and integrated into a running Max install. And the blocks package consists of a bunch of objects that represent different elements that you can put on a Rolly block, which, if you haven't seen it, it's this light pad thing. Here's one of them. And the basic thing about the design of this was that you make like this thing that you see, the little dots thing. So that's like a design of the thing that would eventually appear on the LED surface of the block. So you can basically design just by mirroring rather than having to write code directly to make that happen. So that's cool, but what's not cool is that you can only use this thing in Max. And there is actually a round trip between when you touch the block and then when you get the visual feedback on the block. So it has to take the touch from the surface of the hardware, send it to the computer as MIDI, then Max thinks about it and sends back the changes of the LEDs that would represent what that touch means. So that can be a bit slow. And just so that you have some good jargon here, the fact that this package only works in Max and you can't actually take the interface that you design and use it in other contexts, we call this more generally the trapped in Max problem. We have a solution, we think, to the trapped in Max problem, which what we're looking at is turning Max patches into source code. And we call this code generation, which may confuse you because in a compiler, the last step is called code generation, but that's not what we mean. We actually mean writing computer programs that write other computer programs. So we're actually generating source code, not object code. The first example of this that came out in the world was in 2011, this DSP language that we created called Gen. So in the left side of this slide, you see something that looks like a Max patch, but is actually a Gen patch. And you can see there are mathematical operations, definitions of parameters, inputs and outputs. And then on the right side, that cryptic looking code is this thing called Gen Expr. So the first stage of our code generation is that we turn the diagram into this Gen Expr code. And then from there, we actually generate C++ code. And the Gen environment inside Max is constantly regenerating the C++ code as you change your patch. And it uses LLVM to compile that code and actually just jump to the starting address of the machine code dynamically within the environment so you can actually hear what you're making. Shortly after we released the first version of Gen, we allowed you to export the C++ code. So people have started developing VSTs, iOS apps and stuff with the DSP code that they make in Gen. It doesn't make a user interface for you. It just defines the parameters. You have to glue your own user interface to the C++ code. And on our GitHub page, you can find lots of examples for everything from the iPhone to the Raspberry Pi. So why is code generation interesting? So for me, the big thing that's cool about this is that you can stay in the problem space. So the idea on the left here is like, this is the problem space. Oh, I want to have some parameters and I want them to like look a certain way or be presented, and I can keep in that problem space. And as I'm messing around in that space, code is being written behind my back, and we can actually optimize the performance of that code, and you don't have to worry about that. You just work in the problem space. And the idea is that this means that you can focus on what things sound like, what they feel like, and not have to be worrying about what the code looks like. For me personally, if the moment I start worrying about, what member variables my C++ class has in it, I've stopped worrying about what the algorithm sounds like or what the experience feels like. So the longer I can stay in the problem space, the better. Another thing about generating source code in this way is that you could be a designer, and the square person on the left is supposed to be the designer, and the round-headed person on the right is the software engineer. And because you're both ultimately writing code, the designer never has to stop designing, because in some way the code that the designer is generating matches with the code that the software engineer might need to write that the generation doesn't do at this point. And so what does that mean? So if you were at Friedemann's talk, you heard that they had to design this elaborate process by which they took their original idea, which was in Max, and kept turning it more and more in a manual process into C++ code. So that would, in my dream, that would never need to happen. because the part of the unit, let me back up and say, that's cool, but what's the big problem with that as well? The moment that you commit to writing C++ code, the designer has no way of changing what the thing does, right? You've basically printed this thing in some way. And so now the cost of changing the design gets incredibly expensive because the designer and the software engineer who translated the design into code have to have a conversation. And of course, since the person who wrote the software feels like they have invested themselves in a process, which now they feel like they need to throw away, that conversation's probably not going to go so well. But if the thing that's translating the design into source code is just a process, then that conversation looks invisible in some way. So why should we generate code for hardware like this? So one reason is that typically in a embedded or hardware context, the amount of space you have to have some kind of elaborate runtime environment, for example, maybe trying to port Macs or something like it onto a little piece of hardware like this with very much memory, would consume a lot of resources. This picture, which may not be clear to you, is actually a multi-screen installation that was done with Macs. And what seems to have happened, if you can look at the error message, it says Macs runtime quit unexpectedly. So this is an example of what happens when your runtime environment crashes, and the illusion that you had this cool interactive multi-screen environment goes away. Not having to develop and maintain an elaborate runtime environment, but still giving you this benefit of staying in the design space is a big thing that's important to us about code generation, which is that we can still prototype, but the thing that we get has no dependencies on a big environment like Macs, and we can put it on little pieces of hardware. Another thing is we can have the same design space and lots of hardware targets. So if I want to take my DSP code and I want to make one thing, which is an iOS app, one thing is a VST plugin, and one thing that might run on a embedded hardware like a Raspberry Pi, it's the same patch. I can, in the context of generating source code, change the details, but in terms of what the algorithm is and how I designed it, it can be the same. And finally, this is not something that I'm going to demonstrate today, but is another aspect of my fantasy about this, which is if you are trying to figure out what's going on your hardware, one of the problems is that once your thing is in machine code or in the sort of operating environment of the hardware, usually hardware doesn't come with its own debugging capability. So first of all, because you were able to develop the design interactively, you probably had the opportunity to preview what the thing looked, sounded, and felt like on a computer like this, which is easier to deal with than a small piece of hardware. So at least you know that at the level of the problem, you're probably okay. But then the other thing that you can do is you can actually generate special code. So why not, if you're generating code to do DSP, why not generate DSP code which includes its own ability to report about what it's doing back to the computer? That allows you, for example, you might be able to see audio metering of what was actually happening on the hardware within the creation environment that you're using on the software. Or if you're concerned about the value of a variable, you could just point at the variable and see what its value is. And you don't have to know anything about how the hardware actually is doing this. It just sends this kinds of communication back to you over a network. And the thing that makes this possible is that you basically parameterize the code generation on what you care about. So if you care about debugging and not performance, then you just generate debugging code that goes along with the rest of your code, and it's like integrated into the actual code that you're writing. Once you've got your thing actually working, then you can just get rid of that code and write really hard to read, high-performing code. Okay, so I'm going to talk about this specific thing, this specific little project that I did. So if any of you were here last year, you may have heard Jules' amazing talk about how he developed his own computer language for to define the behavior of this block. And so I look at hardware in terms of like, what's the raw capability that I can do something with that was never intended from the beginning? So here we have a multi-touch surface. It talks MIDI back to a computer, and it has its own programming language. So that's really a cool thing, and there's lots of amazing things you could probably do with that weren't anticipated by the original design. So the block has two ways that you can interact with it. So the one on the left, which is called API mode, you basically write and subclass and use juice classes that allow you to define how touches are interpreted, how the LEDs light up on the screen. And all of this behavior is kind of a circular, kind of two-way interaction between the program running on your computer and the firmware running on the blocks. So at the most general level, what you're really doing is downloading a Littlefoot program onto the blocks, but the program that we use in Macs is basically called the LED grid program, and pretty much all it does is it reports the touches that come from your fingers when you touch the surface, and then it lets you set individual LEDs to specific colors. So we did everything in the blocks package that way. The second way that you can interact with a block is just to write a program in this language, Littlefoot, and basically define what its behavior is. So the goal of this little demo that I'm going to give you is that we wanted to take the same interaction that we created where we had modular hardware and modular software, and how could modular software kind of define the behavior of the modular hardware. But instead of doing it with API mode, we're actually going to generate a Littlefoot program and have the behavior completely on the block, and then you can just unplug the block from your computer, or more importantly, unplug it from Macs, and then use it in whatever context you want. So here's the basic structure of the Littlefoot program for a block. There are really four things that you need to worry about. One is, how are you going to handle touches? So you're going to do something when you get these touch events, and then in Littlefoot, every variable is pretty much global, so you're going to set some kind of global state. And then the repaint function is called about 30 times a second, and it can do something to set the LED pixels to certain colors to respond to whatever that global state is. And I should also mention another thing that you might do when you're responding to touches is send out MIDI controllers so that the block actually does something. But the most important thing is that you want to have some kind of connection between what the person touching the screen does and what the screen looks like. Okay, so I need a volunteer to come up, and would you be interested in doing this? Yeah. So you have to. So you have to stand about here for the purpose of the camera, and then the actual camera that's going to be, you're going to actually be on camera, and you have to hold the block like this so that the orientation is the same as the orientation on the computer. And then you have to somehow look at the block, and you'll see that there's going to be something on here, and you have to, it's like a slider, and you'll have to move it up and down. But at other times, I'm just going to, the reason I want someone else to hold this while I'm operating the computer will be obvious in a second. But so stand a little closer to me. All right. So, okay, so now I'm going to launch Max here. Okay, look at that slick setup where you can see both the hardware and the software at the same time. Okay, so this object, first we have to turn this on. Okay, so you can see that it's found the light pad block. This object is called block stuff. Oh, this always happens, right? The demo effect. Okay, I have a flaky USB connector on my computer, and it only gets flaky when I'm doing a demo of this for some reason. Okay, so this thing is basically a representation where you can lay out a user interface on the block. So I'm going to make a really simple one with this one slider. And you'll see when I drag the slider onto the thing, there's a version of it. Okay, so this is the, so now you can move this up and down. You have to really press, it lost its connection again. Let's try this. Okay. Now. Okay. Really, you have to really press on it. There you go. Yeah, okay. So you can see, so this is the old way. So it's actually, his touch comes via some MIDI, magic MIDI message, system exclusive to the computer. It comes back, I know it. And then Max sends it back. Okay, so now we're going to, if I can get this to work, let me try this one. Sorry. That looks good. Okay, so now I'm going to do is put this into code generation mode. Okay, so now the same exact program has been generated and sent to the block. And you can see the program here. Sorry, I'm making you hold this while. All right, so so this is the program that was generated by looking at that patch. And so, for example, you can see in the, where did I want to see this? As an example, here, it's probably hard to see that, but here's an example where there's an API call in Littlefoot that allows you to send a MIDI controller value. So that currently that is set to MIDI controller 20. And if I go and pick this slider, I can actually change that to, say, 45 or something like that. Now it's actually automatically regenerated the code, sent it back to the thing. And if I look at the code now, you can see that it says 45. So this is an example of like, I basically am programming by like filling out a form. I know that's what Microsoft wants everyone to do, but, also, notice how fast this whole thing is. So watch how fast it regenerates the source code and sends it back to the block as I move this around. So every time I'm moving the slider on the screen, it's actually regenerating the source code and redefining the behavior of the block. That's why I wanted this guy to hold the thing up, because I can't do both of those at the same time. So thank you very much. So basically that's what I wanted to show you. So the larger thought is maybe think about using an interpreted language like this as a way to define hardware behavior, because you look at the speed of the edit compile cycle. It's basically instantaneous, and for hardware, that's like incredible. Is that if you can basically generate code and generate the behavior of hardware as fast as you can move the mouse, it's a little bit faster than most of us are used to for hardware development. And thanks to Jules' brilliant work, it's possible. So thanks very much.
Two quick questions. What's the performance like over Bluetooth rather than USB? And how did you get around the time it takes for the compiler to run? Because if you've got lots of controls in your example, like with one slider, it's not generating that much code. But if you generate a big file, the Littlefoot compiler takes a while to run. Did you do anything to sort of mitigate that?
So the code doesn't actually get that much bigger, and I can't demonstrate to you, but this whole system is limited to a single block right now. So the most number of separate objects that you could probably put in a block is about 14 or something like that. So it really won't get that much bigger. Based on these really simple things, where it's just a one-to-one mapping between a slider and a MIDI controller. And the other thing is that API mode for the blocks is really only a USB kind of thing. So the idea here is we're generating the Littlefoot code so that you can then unplug this and then use it as a Bluetooth thing. But in terms of how it interacts with Macs and its programming whole thing, you would do that over USB. I don't know if that answers your question, but the performance is going to be the same whether of the actual Littlefoot program once it's actually generated.
Yeah, because I was kind of thinking about the actual upload time of your Littlefoot program, because obviously the Bluetooth LE spec doesn't allow high speed like USB does.
More questions? One down here.
Thank you for the presentation. Can you edit the behavior of any of these pieces of blocks? So if you edit the behavior, can you then create like? Oh yeah, I mean like in the background, as in the building blocks of these small blocks themselves. So instead of having a slider, you change it to something else. Is that possible?
Not with what I've done so far. So you basically have to lay out a fixed UI. Okay. That's kind of one of the ideas behind this is why not just generate constants, right? If your UI isn't going to change, then your program is kind of unreadable because it's just a bunch of constants saying where everything is on the screen, but you never had to read it.
Okay.
right? But you didn't need the flexibility to begin with. So why did you make the things the variables in the first place?
Okay, thank you.
So if you actually looked at the code, it's just a lot of numbers all over the place. So in that way, it's not very flexible yet.
Any more questions? Okay, I think hand went up at the back first.
Hi, thanks for your talk, first of all. Really great. A bit confused, so I just wanted to clarify the stack. So it's based on gen that generates the code, no?
No, this is
Okay.
this is actually, okay, here's the, don't plug your ears. I'm actually just using printf to generate the code.
Sorry, again?
I'm just using printf to generate the source code for the most part.
Could at least use std out.
But source code generation is just some kind of templating or whatever. So, for example, I just look at where the position of this box is on the other box, and I generate constants that corresponds to that, and put them in parentheses with commas between them, stuff like that.
So I've just had a glance at the GitHub, at your Cycling'17
no,
GitHub, and I was thinking,
no, this is, so yeah, it's unrelated to Gen in the sense
Okay.
it's just conceptually similar. Like,
yeah,
idea.
but how can we play with it? Like with this piece of software that we are seeing now, is it like?
Oh, I haven't, so this is just a prototype at this point.
Okay, I see.
But at the next version of this package, we'll have code generation.
Okay, perfect. Thank you.
Sorry.
One more, maybe? Down the front.
So I'm just curious, the block where you have the code now on it, I can use this directly as a MIDI controller with this controller 45
Yeah, so now
in Ableton or something?
Yeah,
Is
I
it
just disconnected the thing,
See?
and it lives
Yes.
on here, and
it's
it's
just
looking
fine.
for Bluetooth, but see, I can actually use it.
Yes, great.
So, yes, and it would send out controller 45 or whatever.
And is some more code generation planned in the future of Macs for
Yes.
patches?
Yes.
Oh, wow. Great.
Okay, and I think we're everyone now, so that now is a break, and the next session here is at what time? At 4. Okay, and I think that's the legal panel, which should be interesting. So break time now, and thanks once again to David Zicarelli.
Thank you.